I always do. Okay, here we go. So, in the last two lessons, we have looked at ions and cations, anions, electrolyte, all those sort of things. We have looked a little bit at Faraday's law. We will have a look at that again. So, today we are going to finish by doing industrial electrolysis, that is, production of sodium and chlorine, purification of copper, and production of aluminium, those three. But first, it is always a good idea to go back and remind ourselves to make sure that we can do what we thought we could do before. So here we are. Come on, slideshow, wake up. Okay. So this is more practice before we move on to something else. So we're going to start by asking you to remind yourself that you can write the equation using electrons for what happens at electrodes. So what I'd like you to do is just get a pen or pencil and a piece of paper, or you can do it in your mind and just see if you can do these. I'll remind you of just one of them. So remember, you have to be very careful with the charge. But so, for instance, with a 1 plus charge, we said that we only needed an electron, and that would make it neutral. Okay? So if you do just a couple more, just to make sure you can do that, and then we will do some negative, some anions. Remember, these are all cations. Remember, they're all cations because they're all plus. We said we write it like this to remind ourselves because there's a plus in the middle of cations. Okay, so these are all cations. So just spend a moment, please. Write a few equations like my top one here. Okay, everybody just have a go. It'll only be like 1 or 2 minutes and then we will move on. Hello, Osharika. How nice to see you. Well done for being here. That's great. So I hope you are having a go at writing these equations. I can see some people at Mathari, some people at St Mary's are. Silver Spring, are you going to have a go? Usharika, I think, are having a go. Wamuini, not quite so sure. Are you writing down, Wamuini? That's great work, Mathari. Thank you very much. Okay. What's your name, please, student at Mathari? You're obviously very good. A student who just showed me their answers at Mathari, you could always go back and help other people. A little bit further away, Wamuini, please. Yeah, show me again. Show me again. Little bit to your left. You're a bit too close, Wamuini. Yes, Mathari, they're all correct. You could show them to somebody else. You could see if they can do them. Down a bit, please. Sorry, up a bit, Wamuini. And up a bit more. Wamuini, up a bit. Okay, we need numbers. Okay, everybody. So we're going to just share now. So all you have to do is to remember that you need the same number of electrons as the positive charge. So this is 1 plus. It's not the usual copper 2, so it will need just one electron. Potassium only one electron. Aluminium 3 charges, so 3 electrons. And copper, in this case, 2, so 2 electrons. Okay, so try to make sure that you know that's what's happening. Is this oxidation or reduction? Well, if you remember oil rig, this is gaining electrons, isn't it? The sodium is gaining electrons. So reduction is gaining electrons. So all of these are being reduced. Okay, let's look at the next slide. Let's just get rid of those. Next slide. Okay, these ones are slightly more difficult in some ways. We look at the charge and we say, okay, look, that's 1 minus. So each chloride needs to lose one electron and it will turn into chlorine. The problem is that chlorine goes around in pairs. So we would need 2 of these, and therefore to balance it, it would be minus 2 electrons. Or we can write Cl minus turns into Cl and an electron. It still needs to be Cl2, so still 2 Cl minus and 2 electrons. This is a slightly better answer, really. Okay, so have a go at those. Don't bother doing the bottom one. I will show you the bottom one. So see if you can do bromide and oxide. Just see if you can do them. Everybody see if you can do it. We're moving on in just a minute. Wow, Silver Spring, show me again, please, Silver Spring. Sorry. Nearly right idea, but bromine, the product, and oxygen, the product, go round in pairs, don't they? So it would have to be Br2 and O2. So you will need to put that in and then balance it. But otherwise, yeah, right idea. One more in, show me. Wow, I think you're right. Little bit closer. Little bit closer. Did that say Br minus plus electrons or minus electrons? I think minus. Was it minus? Yes, if it is, yeah, yeah, great, fantastic. Well done, Wamarini. Well done. Very, very good. Usharika, anybody going to show me an answer? I hope so. St. Mary's? Silver Spring. Right idea, but now the electrons are not quite balanced. You've got the right idea now. You need the electrons to balance as well. Well done, Mathari. Very good. Yep. The chloride, we need, it needs to be 2, but otherwise it's okay. Okay, let me show you. So we don't spend too much time here. So bromide, 1 charge, will turn into bromine atom and an electron. But bromine, most of these go round in pairs, so Br2. So I would need 2 Br minus, and that will mean I will get 2 electrons. Same here. This will become O and 2 electrons, but it's got to be O2. So it's got to be 2 O's, and that means it's going to have to be 4 electrons, not 2, 4 electrons. This one at the bottom is more difficult. It forms water, you may remember from last time, and oxygen. And it balances with 4 of these. So 4 of these is enough to make 2 waters. And if it's 4 with 1 minus on each, it'll be 4 electrons. Okay, so these are all anions, and that is what is happening at the anode. Okay, I hope that's all okay. All right. Now, then we looked at aqueous solutions, and we said that there was a way to remember what would be produced in aqueous solutions. If the metal is less reactive than hydrogen, then the metal will be produced. Now, in the first lesson, we said you had to remember the reactivity series, which is like this. Now, there's hydrogen. So if we have something which contains, for instance, if I have zinc chloride, AQ, then I will have zinc ions and hydrogen ions, and the lower one is produced. So there's zinc, there's hydrogen. So this will give hydrogen like that. Okay. Obviously, 2 of those, 2 electrons. Okay. All right. So you need to remember this, the reactivity series here. Potassium, sodium, magnesium, aluminium, zinc, iron, lead, hydrogen just above copper, silver, and gold. Okay, let me just remove that. So that's how we know what cation will be produced. And in anions, if it is a chloride, chlorine will be produced. Otherwise, it will be oxygen. Okay, chlorine or oxygen. So if we had something like copper chloride, that will produce chlorine, but copper sulfate will produce oxygen. Copper, let's say nitrate, will produce oxygen. Copper ethanoate will produce oxygen. In other words, we get oxygen every single time unless it is a chloride. Okay, if it's a chloride, we get chlorine. Every other time we get oxygen. Okay, so let's move on. So now I'm going to ask you to predict what will be produced in a couple of these. Okay, so what will be produced? These are all liquids. Just take 1 or 2 and see if you can see what is produced. Now I'll help you with the first one. Remember that they are liquid, and so the only ions present will be Na plus in this case and Cl minus. So at the cathode, the sodium will go. So the sodium will pick up electrons and form sodium. At the anode, we have Cl minus. So we'll have Cl minus turns into chlorine. And we haven't got any choice, so we get sodium and chlorine. Now, what I'd like you to do is not worry about the equation, just worry about what is the product, okay? So pick any 2, copper bromide, silver chloride, magnesium iodide, zinc chloride. Just find and decide what is being produced. Okay, so I wouldn't write this. Let me just see if I can get rid of that. So I'm not interested in any of that. I'm only interested in sodium and chlorine. There, that's all I'm interested in. Okay? That's what I hope that you will be able to write. Have a go. See if you can tell me what is produced. If it is liquid, there is no water. There cannot be hydrogen or oxygen. We will see aqueous version in just a moment. Just have a go at a few of those. Anybody want to tell me what they think will be formed? And that's correct for the first one. Yes, St. Mary's. Potassium oxide is correct. Potassium and oxygen. Well done. Good. Excellent. Silver Spring have suddenly turned sideways. Oh, hello. Ah, Silver Spring have stopped lying down. Good. Let me just have a look at yours. Up a bit, please. Across a little bit more, Wamuini. That's really good. Very, very good. Well done. Yes, exactly right. Well done. Busharika, correct. Potassium and oxygen. Good. Excellent. Mathari, absolutely, absolutely correct. Well done. Yes. Yes. Okay. I think everybody is getting this. So I will just fill in the answers so you can see what we are getting. So in each one of these, we just have the ions which are in there. Sorry, Wamuini, let me just have a look. Really good. Yes. Yes. Good. Excellent. So what I think you're very good at this. Well done, everybody. So potassium and oxide. Copper is here. It's copper 2 and bromide and silver 1 and chloride. And down here, magnesium 2 plus and I minus and zinc 2 plus and chloride minus. So in this first one, I'm going to get potassium and oxygen. In the second one, copper and bromine. In the third one, silver and chlorine. In the next one, magnesium and iodine. And then finally, zinc and chlorine. These are quite simple because we don't really have an option on any of these. So let's try some which are more difficult. These ones are aqueous. So I'm going to show you how this works so we can remember. I'm going to write the reactivity series over here again just to remind myself. Okay. So in the first example, let's take the sodium chloride. I know I've got sodium and I know I've got chloride, but because it's AQ, I also have H plus and OH minus. Which of these two are made? Well, it's the one which is lower in the reactivity series. Sodium is up here, hydrogen is down here. Hydrogen is obviously lower, so we get hydrogen. At the anode, which one of these? This one would give chlorine, and this is the one which is quite difficult, which produces oxygen and water. Well, the rule was if it's a chloride, if Cl minus is here, we will get chlorine. So it's Cl2. I'll do one more. I'll do copper sulfate. So here I have copper ions, and because it's AQ, I have hydrogen ions, and I have sulfate ions, and I have OH minus. These two because of water. At the cathode, the less reactive is discharged, is produced. Here's hydrogen, there's copper. Copper is lower, so I get copper. On the right-hand side, question, do I have chloride? No, so I get oxygen. It's that simple. You can go, oh, that's easy. Yes. So oxygen, really simple. Every time it's not a chloride, we get oxygen. Okay, what I'd like you to try and do is the two at the bottom. Okay, magnesium sulfate and zinc chloride. Okay, magnesium sulfate and zinc chloride. What will be produced? Just have a go at those, please. Magnesium sulfate, zinc chloride. Everybody have a go. Remember, they're both AQ. Anybody want to show me what they think could be produced? If you're not happy, in a minute, I will try and show you. Show me, Sharika. We're not, you're correct about magnesium. We will get magnesium, but we won't get sulfate. We only have an option of oxygen or chlorine. It will be oxygen or chlorine. Which one do you think it will be? Well done with the magnesium, though, Usharika. Silver spring, a little bit closer, please. Zinc chloride, zinc chlorine. Across a bit, please. I can't see all of it. Ah, not zinc. Zinc is too high because we have hydrogen, not the sulfate. Not the sulfate. You're right about the ions, Sharika. That's very good. Let me go back a bit. Let me just go back. Magnesium sulfate. Let me see. Across a little bit, hydrogen and oh, correct. Well done. Well done, Mathari. Well done, Mathari. Let me just stop sharing and I'm going to go back one stage. So I'm going to see if I can get away. Okay. So please, nobody else write on this board. Just leave your cursors where they are. Don't touch your screens. Okay. So let us say we have MgSO4 and it's AQ. Okay. Now we know that means that it has Mg2 plus because magnesium in group 2 and hydrogen ions and sulfate ions and hydroxide ions. Sorry, that's not very good writing. So then we have to decide which is going to be produced. Is it going to be magnesium or hydrogen? It is the one which is lower in reactivity series. So hydrogen is lower, so we will get this happening. And that will stay in solution. Of these two, we have never seen that produced. This produces oxygen and water. And it does like this. So we get oxygen. So the rule goes like this. If we look, oops, sorry. If we look at something which is AQ, whatever it is, let's say, let's look at the cation. We always have the metal. Oh, what is happening to my handwriting? And H plus. The less reactive is made. Okay? In the anion, we can have all sorts of things, but if it is a chloride, then it will produce chlorine. But if it is anything else, so that could be sulfate, nitrate, hydroxide, carbonate, and so on, all sorts of things, it will give oxygen. So you really don't have to think about this one. If there's a chloride, it will make chlorine. If it's anything else, it will make oxygen. Okay, so let's just go back. Oh, come on. Really? So let's go back. Oh, where has that gone? What is happening now? What has happened here? Ah, here we are. So let's just get rid of all of this ink just for a minute. I know some of you can do this, but I want to make sure that everybody can, as much as is possible. Huh. Okay. Mute, please. Thank you. Okay. So in magnesium sulfate, down at the bottom, I have the magnesium ions. Why is this not writing? What is happening here? Right. So at the bottom, magnesium sulfate. Here I have Mg, 2 plus, and hydrogen ions because it's AQ. And in the anions, I have SO4, 2 minus, and OH minus. These two are from the water. So we consider the cations first. The lower one is discharged. There's magnesium. Here's hydrogen. So this will be discharged. So at the cathode, we're going to get hydrogen ions turning into hydrogen. At the anode, we have sulfate and hydroxide, and the rule is if it is a chloride, no, this is magnesium sulfate. If it is not a chloride, I will get oxygen. That's it. The next one, zinc chloride, zinc ions, hydrogen ions, chloride ions, hydroxide ions. Zinc is here, so it's hydrogen again. So I get hydrogen. Is it a chloride? Yes. Then I get chlorine. That's the rule, okay? Okay, we're going to move on. So this is the sort of question which you might get asked. It's asking, this is about dilute sulfuric acid. So in dilute sulfuric acid, that is really the electrolysis of water. We dealt with this last time. So we have hydrogen ions and hydroxide ions and sulfate, but that's not important. At the positive, we will get minus this, and this does this equation here. They're quite difficult to remember. At the negative, whoops, at the negative here, I get hydrogen picking up electrons and turning into hydrogen gas. So 2H plus 2 electrons. So name a suitable material for the electrodes. Well, almost always these are simply made of carbon. Some people call it graphite. It doesn't matter. It's the same thing. Then it asks, what is the product at electrode B? Well, electrode B is this one here. So it's the negative one. That will be the positive ions. So what is produced is hydrogen. Write an equation. There it is. H plus electron turns into hydrogen, H2, 2H electrons. What happens to the concentration of the sulfuric acid? Nothing happens. That is because it is the water which is being broken down. Here's another question. You will get these with the answers. Your teachers will get these with the answers. This is magnesium sulfate. Okay, magnesium sulfate. Now, I know this is drawn the other way around. Is it? Hang on. Yes. So you have to just be able to spot that the longer line is the positive one. Okay. So this one is negative. This one is positive. Now we've got magnesium sulfate and it's a solution. So it's AQ. Now, fairly soon, we should be able to work out what's happening. We've got Mg2 plus and H plus, and then we've got sulfate and OH minus. So what does it ask? Name a suitable material for the electrodes. Oh, look, there it is again, carbon. What chemicals are produced? This is a bit of a hint. There is more gas here than there. This is hydrogen and that is oxygen. 2 to 1 because it's H2O. At which electrode does oxidation? Oil rig, or Leo goes, Leo is losing electrons is oxidation. So losing electrons, what loses electrons? Well, that'll be the negative ions. The negative ions will go to the positive and lose their electrons. So it will be the positive electrode. Now, the positive electrode is called the anode. Okay, now we're going to move on because we need to get on to the thing which we're going to be concentrating on today. Your teachers will have these questions. These are straight KCSE questions. The answers will be there. Now, in last time's lesson, part 2 was about Faraday's law, and it was about coulombs. So here was an example where we were asking how many moles of electrons are needed to produce 1 mole of a particular chemical. And I'm going to remind you, Na is in group 1, so it has a charge of 1. That means that it picks up 1 electron to produce Na. So if I want 1 mole of Na, then I need 1 mole of electrons. And 1 mole of electrons is 1 Faraday. Okay? And those are the same. The thing you don't have to remember, 96,500 coulombs. Now, if 1 mole of sodium needs 1 Faraday, then 2 moles of sodium will need 2 Faradays. What about chlorine? Well, chlorine does this to become chlorine, like that. This is why we have practiced the equations. So for 1 mole of chlorine, we have 2 moles of electrons, which is 2 Faradays, which is 2 times 96,500 coulombs. Okay? So here's some for you. Have a go at these. Let's ask you just to do. This is from CU2 plus. Okay, this one, do this one, and do that one, please. Okay, so just try the first and the last questions, and we'll see whether you can do it.
One number two.
You don't have to remember 96,500. They would give you that in the question. It's how many moles of electrons are required. So write the equation first. If you're not sure, whoops, what am there? If you're not sure, I will show those people who are not sure with these two in the middle. So if you're not sure, just watch this. So magnesium is in group 2, so it is Mg2 plus. That means that it will need 2 electrons to produce Mg. If that is true, then 1 mole of Mg, because there's no number here, it's 1, needs 2 moles of electrons. You see, it says 2 here. And so the answer is 2 Faradays. If I look at the aluminium is Al3 plus. So it picks up 3 electrons to form Al. Now, if that is true, then 1 mole of this, then we look back at the electrons. Because there's no number here, that's 1, needs 3 moles of electrons. That's 3 what we call Faradays. Faraday is just a mole of electrons. So has anybody got any idea on what the answer is for 2 moles of copper from Cu2 plus and 1 mole of oxygen? Anybody got any idea? Okay, I'm just going to look, St. Mary's. Down a bit, please. You're right that it needs 2 Faradays for 1 mole, but the question says 2 moles of copper. If 1 of copper needs 2 electrons, then 2 will need St. Mary's. Go and think about it. Yes, Sir Sharika. Very nearly. Very nearly. Very nearly. I'll show you. I'll show you. You're nearly there. You're nearly there. A little bit closer, please. Wamwini. Great. William, how many electrons? 1 mole of oxygen. You've got 2 electrons, William. You've got 2. Al wouldn't be 2 moles. Oh, was it? Sorry, on my equation. Oh gosh. Thank you. Sorry, St. Mary's. Sorry, guys, I made a mistake here. Thank you very much for spotting it, St. Mary's. Look, I'm not even reading my own question. That's rubbish. Here, get rid of that. My question here says, hang on, my apologies. I can't even read my own question. 2 moles of Al. Well, if 1 mole requires 3 moles of electrons, then 2 moles, this is for St. Mary's, then 2 moles would need, whoops, hello, would need 6 moles. Okay. So let me just do it so that we can move on. Okay, so here we go. So Cu2 plus. Cu2 plus picks up 2 electrons to turn into Cu. Okay, so let's just get everything else out of the way because it's too messy. Let's just get rid of all of this. Just move it a little bit. Okay. Okay, so it says 2 moles of copper. There's 1 mole, which needs 2 moles here. So there's 2 different ways of doing it. Either I can say, therefore, 2 moles will need 4 moles, or I could rewrite it. Cu2 plus a certain number of electrons turns into Cu, but I know I need 2 of those. So 2 of those, which would require 4. And there it is. So it's 4 moles of electrons or 4 Faradays. In the last one, O exists as O2 minus to form oxygen and therefore some electrons. So we're going to need 2 of those. And because they're 2 minus each, we're going to lose 2 times 2 minus 4 electrons. So 1 mole of oxygen is going to need 4 moles. Okay, 4 Faradays. Okay, let's move on. So let's try a question. Actually, no, we'll move on. We'll move on because I want to get on. You can come back to this later. What I'm going to do is I'm not going to show you how to do this right now. We can do it later if we have time. I want to look at the main uses of electrolysis. Okay, the main uses of electrolysis. The first one is electroplating. Electroplating is covering one metal object with a layer of another one. Covering one metal object with a layer of another one. Now, normally we would start with something which was not very valuable. Let's say we wanted some silver earrings. Silver earrings can be quite expensive, but nickel earrings are quite cheap. Copper earrings are even cheaper. So what I would do is I would get some copper earrings and then I would plate them with silver and I would sell them and people would go, hey, they look like silver. And actually they are copper with a very thin layer of silver on the outside. So electroplating is covering one metal with a layer of another one. It's normally something like silver and gold. The next ones are all about getting hold of something expensive, extracting it from a rock. Now we're going to go through this in a bit of detail. We've got aluminium. Come on. What is happening? Oh, my slides have stopped. What is happening? Oh, right. I'm going to show you how to draw this. It's more important. This is a simple version of that. Here's a question about it, which we will look at briefly. Here's the use of electrolysis for splitting sodium and chlorine in molten sodium chloride. There's a question about that. And then here's one for purifying copper, which is slightly different from the other two. And that's where we will end. Okay. So this is aluminium electrolysis. And what I'm going to do is I'm going to show you what happens in this. If you look at this, it's much more complicated than this. So I'm going to tell you they often show this is an exam question. So I'm going to tell you that the one at the top is plus, and then the one at the bottom is minus, and that is the whole of the bucket, all of this, all the way down here, all the way along the bottom, the whole thing, all the way up here. It is all negatively charged, okay? In here, we have aluminium oxide. Now, aluminium oxide is aluminium ions and oxygen ions, Al3 plus and oxygen 2 minus. So there are two of those and three of those. And that's what we have to think about. Okay. Now the Al is charged plus. So it will be attracted, the Al3 plus ions will be attracted to the bottom. When they get there, the Al3 plus will pick up electrons and form aluminium. And because it's very hot, we get a layer, all of this in here is aluminium and it comes out here. Okay. Now, at the same time, the oxygen is discharged. Now, the oxygen is in here at the top here as well. So we've got O2 minus. Now, the O2 minus will be attracted to, because these are all plus, obviously, be attracted to it. Now, the O2 minus turns into oxygen and electrons like that. Okay, so that's the main process. So let's have a look at the question. Okay, we'll go through it a bit more, but that's the basis of it. The aluminium ions are attracted to the whole of this outside here. This is actually carbon, but with an iron core, an iron bucket round it. Each one of these positive electrodes is made of carbon. Okay. On the diagram, label anode, cathode, and electrolyte region. Okay, let's go back. So I'm just going to get rid of all of the ink so far. So it says, what is anode, what is cathode, and electrolyte? Now, if you can't remember with this sort of thing, if you can't remember, is this plus or minus? Just remember, cation is written like this. And the cation goes to the cathode. Now, if that is true, then the positive ion will go to the negative electrode. Okay, so the anode and the cathode, there we are. We can get those 2 marks because back here, positive must be anode, cathode is negative. So I go, okay, I have to remember that the top one here, this is plus. What is happening? Why is my pen not working? Oops, hello. Let me just get rid of that. Okay. So you need to remember that that is positive and this is negative. So cations are positive and go to the negative. So that is the cathode. And these are the anodes because there are lots of different ones of them, okay? But they're all charged plus. The next question, oh, an electrolytic region. Well, the electrolytic region is just where the electrolysis happens. So this is the electrolyte. Okay. Next, the electrolysis is uh, really hot, 900 degrees, but the melting point of aluminium oxide is 2054. Why is it not carried out at 2054? If they ask a question like this, it is always the same, and that is, it is too expensive because heat needs energy. Well, energy is very expensive these days. What is done to lower the temperature? Okay, the other thing you need to know about this here is that in the electrolytic region, there are two chemicals, not just one. We said there is aluminium oxide, but there is something else. Does anybody know? Does anybody know the name? It starts with a C. Anybody know it? No? Okay, it's cryolite. So in this, in the electrolytic region here, we have Al2O3 and something called cryolite. Cryolite, the mixture of aluminium oxide and cryolite melts at around about sort of 900 degrees Celsius. That's great because if it was pure aluminium oxide, it would be too high for it to melt. So we do it much lower because we add cryolite. So basically, we add, whoops, cryolite, the Al2O3 and cryolite mixture melts at a lower temperature. Okay. Okay, so there's an electrolysis question about aluminium oxide extraction. Let's move on. This is sodium chloride. So we've got molten sodium chloride, NaClL. So we must have sodium ions and chloride ions. This must pick up one electron and form sodium. This must turn into chlorine like this. So the chlorine comes out of the top here. And the sodium, it basically, because it's not very dense, this is the negative here. This is negative, and it's like a ring. It's like a U shape. Okay, it goes all the way around the back. And that means the sodium is formed in here, above here. So the sodium floats to the top here. Floats to the top, is trapped. Okay. Here's a question. It looks a little bit different, but it's not. It shows you which are negative and which are positive. That's negative. Here's positive. So in this particular example, they've got a gauze here. Now, what a gauze does is to separate the two products. Okay, one of which here is caught here, and this is the sodium, and the chlorine goes out the top here. Okay, there's sodium there, and there's sodium here because it's right the way round. Okay, it's a circular system. Now, why is the anode made of graphite instead of steel? Well, the reason is if the anode, that's the one which the chlorine was produced at, was made of steel, the iron would react with the chlorine to form iron 3 chloride, like that. Okay? And how are the electrolytic products separated? It's this gauze. They are kept separate with the gauze because otherwise they would just react together. This is quite hot. So if I had sodium and chlorine, they could react together if they could get together to form sodium chloride. That's no good. I'm trying to make sodium and chlorine. Okay. And finally, purifying copper. Now, purifying copper is a little bit different, but I'm going to just show you it very, very quickly. It goes like this. I get a big container. In one end, I get some impure copper. Here's a lump of impure copper. I attach this to a power source. In the other side, I get a piece of pure copper, very small to start with, but pure. So that's pure copper. And this is impure copper. Now, what happens is that this is the positive and that's the negative, like that. Oh, no, sorry, I've got it the wrong way around. Huh, stupid. Hang on. Oh, my apologies. Oops. Can't write with the rubber. Nearly finished. Hang on just a moment. That's the positive and this is the negative. And what happens is that the copper in here dissolves to make copper ions, loses electrons, and then these copper ions go across and stick on here, picking up electrons to form copper. All the impurities drop to the bottom. So that's how it works. Now, we might run through this briefly, this industrial thing again next time, but it's time to stop now. It's virtually past. So I will say thank you very much for being here. I'm going to stop recording.